Boom. Good morning, everyone. We'll start in a few minutes. Okay. Good morning, everyone. How are we doing today?
Good, and you?
Not so bad. Well, hope I'm looking at the window right now, and oof, not the nicest weather. Well, on that note, yeah, let's just jump right into it. I'm just gonna review the stuff that we've learned so far for optics, and maybe do some questions. I see I have a question here about one of the OpenStax stuff, so I'll get to that. But yeah, I'm just gonna start off by reviewing everything we've learned, at least that's gonna be relevant to the stuff on the midterm. I put up an equations formula just now. I was kind of debating how much to put on it because some stuff does kind of give a lot away. So someone's asking what chapter the exam is on. There's a file on your Omnibox that tells you all the topics that are being covered. So I encourage all of you to look that up. And yeah, so I also put up the tutorial slides. I put up the formula sheet. So let's see. Right, yeah, this is the formula sheet you're gonna get. So So you probably might realize that it doesn't really have everything. You can use whatever formulas you need to, not just the ones listed here, obviously. And you're going to have to, because this doesn't have everything you're going to need. A lot of the formulas, like thin film interference or single slit diffraction, if I put them here, we kind of give gives the whole question away. So this kind of has like more basic stuff, but you don't really have to show any like hardcore like derivations to use other formulas. Just know that they're not all here in the formula sheet. So these last two formulas, by the way, are talking about phase difference. This may or may not be relevant for the bonus question, who knows? But basically it's saying that if you have two rays, they're arriving at a point, what's the phase difference? Well, it depends on three things. It depends on, what phase they were emitted at, what's the phase difference when they're emitted, what's the path length between them, because that affects phase, and lastly, what's the time difference, because that's also going to affect, right? At what time are they arriving? If there's a time offset, that's also going to affect the phase difference. And lastly is a formula that lets you figure out what the phase difference can be when there's a path difference or when there's a time difference. So you can find the path difference, sorry, the phase difference, you can find that when there's like a length offset or a time offset for two sources of light meeting at some point. So we haven't really talked about that too much, but it makes sense that if two light beams arrive at a point and there's some distance apart from each other, that makes a phase change. That means there's a path difference. It's the same thing with timing, because if they are being emitted with some different kind of timing, it means that they're a different part of the cycle when they arrive at the same point. So that is going to affect the phase that they arrive at, and that's going to affect the interference. Somebody asked me if we need to memorize the formulas that don't appear on the sheet. I mean, yeah, I don't want to say you have to memorize them. You just really I mean, yeah, I guess you can say, yes, you're effectively memorizing some stuff, but I mean, it kind of, once you get like handy with this stuff, it isn't really so much memorization. It's just like, right, recalling the stuff. Like if you're looking at thin film interference and the two beams are coming out in phase, right? Like, yeah, you know that the only thing that makes a difference for thin film, if they're both in phase, is the fact that one of the two beams of light has traveled, the thickness of the film twice. One's coming down and one's coming up. So, the path difference has to be, 2 times that thickness. And you also know that if they're both emerging in phase, then as long as the path difference, as long as the thickness is equal to, some multiple of the wavelength, right, then that guarantees constructive interference between the two rays. But then you also think about the fact that, well, the ray that's inside the film that comes back out, inside the film, its wavelength does get changed because it's entering the film into new medium. So you're not quite using the wavelength that you're shown in air, but rather you're using the wavelengths in the film. So if you write that out, it will be m times lambda divided by the index of the film, because you're traveling inside the film where the wavelength is different, so that's going to shift things. Of course, when you come out of the film, that you're back to your regular wavelength, so you're not really worried about that. It's just inside the film that the path difference has to account for the wavelength in the film, as well as the fact that you're traveling basically twice the thickness of the film to come back out into the air. So do you want to memorize this? Well, if that's your last research, but I'd argue that, yes, that's that formula you should know, but also you should understand it too. So I don't want to say memorize it so much as know the formula, but also know where it comes from. especially because there's two cases, right? There's like the thin film where one gets reflected out of phase and the other one doesn't, and then there's one where they are both in phase. That's gonna change which formula you use if you're looking at constructive or destructive interference. That's probably one more formula you want to keep in your pocket for diffraction stuff, which we'll talk about when we get to that. And other than that, be careful, obviously, when you're looking at lenses and mirror questions, that the focal length, the sign on the focal length depends on type of lens and mirror. So also I put up the slides doing the recap, which I'm going to get to now, but it's on Omnibox as well. You want to unload that now and follow along. Anyways, I'm going to jump into it myself. So let me just... Where am I? Ah, yes. Okay. Found it. So yeah, I'm just going to jump into the tutorial now and just get on with the show. Yeah, okay. So we got about like 5 chapters of optics. 5, no, 4, right? Because we're doing 35 through 38, at least in my textbook. Basically starting off with the basics of reflection and refraction, then going into the double slit diffraction stuff, going back to reflection and refraction with lenses and mirrors, and then going back to diffraction. So anyways, taking from the top, when it comes to reflection and refraction, light can be dealt with what's called array optics. And well, you know, to explain stuff like the interference pattern, you need to think of light propagating as a wave, as a ripple in space, you know, projecting onto a screen. When it comes to the effects of reflection or, you know, refraction, like bending away when you stick a straw in water, it turns out that you can actually describe it pretty well with just drawing the propagation of light as just a bunch of arrows. The fact that light can act like a wave doesn't really factor in the physics of reflection and refraction. So ray optics simplifies how we look at light. And that's why it's called a ray approximation, because we know it's not really just a ray, but it's enough to explain optics. So here is an early preview of the effects of diffraction. So basically it's saying that given a spacing that's small enough, the light that comes on the other side basically emerges as if the slit was a point source. The principle of that is kind of solidified by Huygens' principle, where it basically says that you can consider, if you stop time and just look at any point where light is moving, you can treat that point as a point source, as you know, it's like a point where like a ripple emerges, and any future propagation of light can be seen as just the superposition of all these point sources at present time. Anyways, so with that principle, you can determine that, yeah, if you send light through a big slit, it's just going to pass through like a big funnel. But if the slit is smaller and smaller, then the funnel now acts kind of like as a point source, and you know, you get like a ripple coming out. You can actually observe this too if you do this with waves. So if you can imagine like water being sent through a small opening on a dam, you'll see the exact same effect if you make the dam gate smaller. Anyways, so light reflects off surfaces. Ideally, it reflects in a predictable way. That's called specular lighting. Sometimes it doesn't, and it goes off in all directions, which makes things kind of causes glare. You know, if you were looking at a textbook under light, kind of glares at you. That's because light isn't bouncing off smoothly. That's diffuse lighting, which we don't discuss. So we're going to discuss ideal reflection, which is things bounce in a predictable way. And the rule of thumb for that is very simple. It's the fact that light goes in at one angle, it comes out at the exact same angle. So yeah, diffuse reflection, we don't want that, we won't discuss it. Oh heck, they use the same example I just gave. So yeah, bathroom mirror, that's speculative reflection, that's good stuff. You can see yourself. Then yeah, light hitting a textbook, it's diffuse. It's when you see this like glare of light that just doesn't make it easy to read under some lights. So yeah, the rain-soaked streets diffuse the light from the sun, while on a sunny, dry day, you can see more clearly. Anyways, yeah, so reflection is fairly easy, right? You have a ray of light coming into a surface, and it's just gonna bounce off predictably. If you draw an angle with respect to the normal, we were used to, in earlier physics, like kinematics, we're used to drawing angles with respect to like an x-axis. But for ray optics, we always draw in terms of so in classic physics, right, we usually consider this angle here with respect to an x-axis. But for optics, we tend to talk about an angle with respect to the normal, a line that's perpendicular to the surface. So the question from Matthew saying, we will need a protractor ruler for the test. No. There's not gonna be like any questions where it's like, oh, hey, you have a mirror here and a mirror here, like a third mirror here, and like you have like a light beam going off like this. That's not gonna be the case, mostly because at that point, you're really just testing like trigonometry and angles. It stops being a physics question. It starts being a math, which I totally think it's a skill, you do want to have, but no, not now, not for this week. There's actually an in chapter. I like the in chapter examples a lot, but there is one for the mirrors, which kind of tends to make the question a bit more confusing, which is disappointing. But anyways, just rule of thumb is you can predict reflected rays because they're going to make the same angle as the incident ray, which makes dealing with reflected images fairly easy to predict. So are you going to have to do a diagram? Yeah, you're probably going to have to draw the lens or a mirror like you did in the third assignment. I think question 4 had you draw like an estimate, not like a perfect ray diagram of a lens, just kind of like an estimate of where things should be. You can probably expect to do something like that in midterm. But you're not going to be like shown like a weird puzzle of light beams and like have to deal with that. Anyways, oh yeah, this is just an example of how some materials are designed to reflect light back at you. So it makes them look shiny, because stop signs right at night, you can't really see them when it's dark, but with these little retroreflector particles, not particles, more like material, headlights from your car kind of gets bounced back. So you get to see the stop sign quite easily. So it's kind of like it's not quite a mirror, since it doesn't show you, it doesn't reflect what's surroundings, but it reflects light in such a way that it makes the surface shiny. Anyways, refraction, even though we can explain it with ray optics, refraction actually occurs due to the wave nature of light. Since we talk about waves, a mechanical wave, just shaking a rope up and down, it can be transferred into other mediums, and there's some reflection happens too. There's a transfer into the new medium, but some of the wave gets reflected back. So whenever you shoot light you're getting some light reflecting, you're getting some light entering the medium. Mirrors are very reflective, so most of the light reflects off. But bright, if you look at anything else though, that's not a mirror, some light gets absorbed into the medium, to the wall or whatever. So this also accounts for this sort of wave model also is going to account for thin film interference later on, but it's just kind of showing you how, due to the wave nature of light, we also we get reflection and refraction. So basically, the light beam that comes in gets reflected. You can predict it with the law of reflection. It's the same angle as the incident ray. But the refracted ray, you can also predict the angle at which light bends. And the reason why light bends is because when it's in a different medium, or when it's a medium in general, light tends to bounce around the particles. The different media can obstruct light differently, but overall, what really sets mediums apart in the way that they interact with light is how the overall traversal of light speeds up or slows down depending on the medium. Generally speaking, light mediums, like stuff that's still dense, like diamonds or water, even just air, light tends to have an easy path getting through. It's not really bumping into a lot. So they move pretty fast. Dense mediums move slower. Due to those interactions, when it enters a denser medium, like you see in the picture here from air to glass, light is going to go slower. And what that results is that the refracted ray, its angle from the normal is smaller than the angle between the incident ray and the normal. So you move into a thick medium, light slows down, and the beam bends towards the normal. The other way around is if you were to travel from a thick medium to a thinner one, like from glass to air, if I shoot a beam like this, the light beam is actually going to bend away from the normal as it enters the faster media. So you can actually figure out the relationship between the angles of incidence, theta1, and the refracted angle, theta2. It's not as straightforward as the law of reflection. It's actually based on the ratio of their sine functions to the ratio of the speed of light in the media. Don't be confused though, because we're talking about the average speed of light in traveling through the medium. The instantaneous speed of light is still c. We're just talking about the total trajectory of light, which is slower due to the bumping around it does. So, okay, the quick quiz here is just showing you how, if you look at the incident beam number 1, just coming into this plate, and you see how some light gets reflected, most of it enters the plate and bounces off again completely in total internal reflection. And then at this interface, it looks like most of it just refracts out. And you can see clearly, right, how like if you look at the angle, of the incidence, it's smaller. The angle that ray 4 makes is, you can kind of tell it's a smaller angle than the angle here that ray 5 makes with normal. You can also kind of tell a little bit between ray 1 and ray 3 that the angle here is definitely bigger than the angle between ray 3 and the normal. And you can also tell that due to the law of reflection, the angle between ray 2 and ray 1 are basically identical. Now, if you do this in the lab, it might be that the angles are not exactly identical because the law of reflection assumes a perfectly smooth surface, and there's no such thing in reality as perfectly smooth, but it'll be close enough. You need like a really, really good protractor to tell anything apart. So, anyways, so So anything else? Right, so rather than talking about the angle of reflection, sorry, the incident angle and the refracted angle as a ratio of the speeds, opticians would rather talk about the index of refraction, because that lets you basically talk about the speed of light in the medium compared to the speed of light in a vacuum. So that's just how fast light goes in a vacuum over how fast light goes in a medium gives you the index of refraction for that medium. In other words, the slower the medium, the higher the index of refraction. There's this like inverse proportion you can see here, where so it's inversely proportional to the speed of light in the medium, which means that slower mediums have higher indices. So that's why if you look at this list here, you have some thick stuff like something that's common, like you know, gallium phosphide, cubic zirconia, like solid stuff have a much higher index than stuff like ice or carbon dioxide or air, so gases. Light has an easy time going through gases because they're so less dense that it's just kind of like an easy trajectory. But then you hit like some stuff like gallium phosphide, and it's so thick that particles of light are just bouncing all over the place. So it takes a while for them to get through the medium, which leads to a higher index of refraction. So by talking about the speeds in medium this way, you kind of get to rearrange that formula we saw to figure out the incident angle and the refracted angle. Now it's drawn in terms of the index of refraction. So this is just the general way to do it. So if you know what medium you're working with, you know the angle of incidence, you can figure out the angle of refraction. Also, it's worth pointing out that when light does enter any medium, when it refracts or whatever, not only does its speed change, but so does the wavelength. You might recall the wave formula, it's always true, that the speed of light is going to be adherent to this formula. So even for light, the speed of light, is technically constant, but we're just talking about the overall trajectory of light. It turns out that, again, it changes speeds in new media, and that means that it still adheres to this wave formula, which means that if the speed of light in the media is changing, either the wavelength or the frequency must also change. And frequency does not change because that's related to the conservation of energy, so that's constant. Instead,
I have a question.
Sorry, someone had a question?
Yes, I have a question. So I was going to ask, would you ask us to calculate the index of refraction, like specifically to the medium, and then compare it to the value, like in the table?
So, like calculate an index and then compare it to the table with the index values?
Yeah, basically.
No.
Okay. But you could give us a question where you ask us like you give us a ray diagram and you would ask us for velocity, wavelength, and frequency. I think I saw ones like this in the book. Like the frequency at which the light travels.
Yeah, I mean, that's possible, but if you know the frequency of the light, I mean, that doesn't really factor into Snell's law.
No, but you can use no. So here's what I mean. You can use Snell's law. You can take the like the n value for the index obtained, and then find I think lambda with it, if I'm not mistaken.
Okay, I guess you're saying that if you know the index of refraction, you know the relationship.
Yeah, you know this relationship, and then you can find lambda, and then you can find the frequency if you have that.
Okay, and then you have, right, you have C is always equal to lambda times F, and speed of light is some constant. Okay, well.
That's exactly what I'm saying.
Okay, so I guess you will have to know the frequency of light, and that'd be a really cool question. I
Yeah,
feel
that's
like,
why I thought of it because I found it in the book. So I was
yeah.
thinking that would be like a good question to put on the test. I don't know, in my head.
So yeah, that is a good question. I feel like, yeah, so this question does combine some of the stuff we've seen in the waves section of the course. So we've seen the wave formula really show up a lot in the like chapters 18 on 19. So no, this would not be on the midterm, since it's kind of like this would be like a callback to earlier stuff. It's going to be a good question for the final though, because it kind of incorporates, it mixes Snell's law with the wave formula from the earlier chapters, but it's not something
Well,
that's
actually, it isn't 35 though. It's 35.4 or something. The question that I found at least. It's not from the other chapter.
right. No, I just mean that like I won't put this on a midterm on this midterm because I argue that the stuff with the wave formula, the focus of these chapters is not C equals lambda times F as much as it is like the ray optics and the diffraction effect. So I wouldn't worry about this happening in the midterm just because it isn't necessarily centered on the main topics of the chapters for optics, which the central point here is, just dealing with the indices of refraction directly in the angles. So we're not really too worried about the lambda F for the purposes of the midterm.
Okay, thank you so much.
No worries. This can be a good idea for the maybe a really cool like question like in a final exam, like just knowing kind of bringing in anyways. Don't give your teachers ideas because they're gonna apply them. I'm kidding, by the way. Um yeah, no, like the whole idea is that indices of refraction are used to make things a bit easier for ray optics, since it lets you it lets you forget about light as a wave or anything. It really just lets opticians kind of look at the table and figure out, okay, well, I have this material with this material with this index, and that's it. You really kind of remove any considerations of like wavelength or frequency from the picture, which as physicists, ideally we don't want to ignore that completely, but for the purposes of figuring out refraction, since it doesn't really, by doing the index of refraction approach, we really get to not worry about wave stuff, frequency and lambda. Right? Because like when you go get your glasses done, we talk about power, we talk about focal length. We don't really worry about light doing its wave stuff, which is why ray optics really tends to do that. Anyways, turns out that light bends away from the normal when it enters a light medium, but effectively, that means that as the angle of incidence increases, so will the angle of refraction. Eventually, though, you reach a point where the refracted light is basically at a 90-degree angle from the normal. So if the angle of incidence even increases even by a little bit, what's going to happen? Light just, it's already at 90 degrees from the normal. It can't bend lower because it would just go back to, right, it would just go back to the original medium it was in. So in fact, nothing's going to happen. Light's going to stop refracting when the incident angle passes some critical angle. To figure it out, you just use Snell's law and you say, well, we're reaching the point where the incident angle is so big that the refracted angle is at 90 degrees. That's that would be ray number 4 in the drawing shown below. So right, that we're moving into a light medium. So light, I mean, you shoot it straight up. Right? It's worth pointing out if you shoot light straight up, there's no refraction, obviously. But right here, the angle, it's always like getting wider and wider until eventually you reach this critical angle where now light is bent at 90 degrees from the normal. Any angle bigger than this for incidence, then light will not refract at all. It's just going to be totally internally reflected. This is not on your formula sheet, by the way, but it's easy to figure out. You just need to, realize that it happens when the refracted angle hits 90 degrees. Also, be careful with degrees. Your calculator has two modes, degrees and radians. I try to be nice with marking, and if I can tell that your final answer had a mistake because clearly you were in radians mode, I'll be fine, whatever. But just be careful with the degree setting on your calculator. Basically, the rule of thumb is if your calculator is spinning a tiny angle, it's probably a big hint that you're getting an answer in radians. If the angle is really big and you're expecting radians, then you're probably in degree mode. Anyways, so obviously this only happens for light moving into a lighter medium, since that's when it bends away. Okay. Anyways, so the double slit experiment is cool because when you shoot light through two slits, the overlapping ripples will create an interference pattern on a screen. And you can actually figure out through geometry where the points are going to be bright fringes and when they're going to be completely dark fringes, or anything in between, actually. So the idea is that if you look at the screen, at different points along the screen, the light coming from both slits travels a different distance, and that determines the phase difference between them, and that's going to determine what kind of interference happens at any point. And yeah, just rule of thumb is you're assuming that the light that enters both slits is from the same light source. That's called coherence. And that's what ensures a steady diffraction pattern, because if you use two different light sources, what ends up happening is that they're not coherent, so they tend to modulate very quickly. So that's, you won't really see a steady pattern. So the setup is just coherent light source. So yeah, different points on the screen have different path lengths, and from just the geometry of the setup, you realize that there's a relationship between the spacing of the two slits, the path length, the path difference, and the angle between a point of interest on the screen and the center of the two slits. And you know that this is the path difference, so you can find out where constructive interference happens, because that's when the path difference is a multiple of the wavelength. And path difference being d sine theta. Also, that means that actually, if you look at it in the center, you're going to have constructive interference, and that gives you then a bright central fringe, which is what you saw on the lab. And if you want to look at points where the fringes are dark, then that's when the path difference is a half wavelength. Note the term here is n plus 1/2. So this makes sure that you're skipping odd. Sorry, this makes sure that the plus 1/2 makes sure that you skip even factors, because if this is even, you end up with the constructive interference formula. So constructive interference is just a half wavelength offset. So this determines the dark fringes, and remember that anything between the dark and light fringes are just some in-between intensity. So here you go. Just talking about the order of the stuff. The index m is centered at 0 and then increases up and down or left and right as you go up, go away from the screen. So the spacing between the fringes, you'll see that it's approximately linear. This formula is not on your formula sheet A, but basically for the small angle approximation, if you look at the setup, we know that the path difference is d sine theta. And if you want to find the position of a fringe or any point on the screen, if you look at the sort of setup that you have, it is a right angle triangle. So the relationship between y and the length of the screen can be expressed through a tan function, where you have y over L. But you are totally good to assume that L is probably going to be a lot bigger than the spacing between the slits and y. So what I'm getting at is that effectively you can get a small angle approximation here, because if L is really big, the spacing between the slits and the screen is really big, basically guarantees that the angle between the center and the slits is going to be tiny. And that's true. You've seen that in the lab. Like, even if you shoot your laser through the slit, like 5 meters away into the wall, the pattern's super tiny. So you can always argue small angle approximation. So with that argument, then, if you break down tan theta, with a small angle approximation, sine theta is approximately theta, and cos theta is just 1. So in this case, the relationship between the vertical position of the point on the screen is very much directly proportional to the angle theta and the length of the screen. But also, while we're at it, right, we did say that the path difference was d sine theta. For a bright fringe, at least, it's going to be m lambda. So if we use the small angle approximation, this becomes d theta m lambda, and we can subsequently write the angle theta being proportional to y over L. Again, all part of the small angle approximation is equal to m lambda, and you end up with y. In this case, this is the condition for a bright fringe, so it's going to be y equals to Lm lambda over d.
Can I ask a question?
Yeah, what's up?
Actually, in the lab, we measure the minimum for the first two parts, but like the equation that Ellie used was the first one that made me really confused, because I did it after the lab, so I didn't have the chance to ask my question.
Right. So at the lab, the reason why we used the first equation was because we were looking at single slit diffraction patterns. Okay. Or, well, single obstacle diffraction pattern in this case. When you have two slits like this, what we're actually looking for is an interference pattern. So these formulas we're looking at now are for the interference pattern, but in the lab, we use the formulas for the diffraction pattern, which are like the mirror universe twins of these formulas. So for the diffraction pattern, the formula we used is that the dark fringes wait, forgive me. Because we're looking at the lab, we're doing like single slit diffraction or single obstacle diffraction. Rather than having D, we have A, which A is either the width of a single slit or it's the width of the obstacle. So that was your graphite mechanical pencil, or it was the width of your hair. And this formula, the way that single slit diffraction is looked at, the way that the diffraction pattern is looked like, it turns out that the position of the dark fringes is based on the same formula that you get the position of the bright fringes for double slit diffraction, right? So double slit diffraction has a formula for its position based on L, M, lambda over D. And the dark fringes of single slit diffraction has the same formula, but it's about dark fringes. Well, for double slit diffraction, it's about bright fringes. So kind of
Thank you.
similar formulas, but one tells you bright fringes, the other tells you dark fringes.
Okay, got it. Thank you.
Did that answer your question?
Yes.
So yeah, so be careful, right? When you're talking about bright fringes for double slit diffraction, and also for diffraction grading, you can use this formula here. But for the single slit diffraction, we only really talk about the dark fringes using this formula. And so if you know how to do double slit diffraction, you know how to do a diffraction grading question because it has certain formula.
Sure. I have a question.
Yeah, what's up?
So say we're asked to find out the y of all of the bright points on the board.
Mm-hmm.
So as you could see in the picture, you have the y only corresponds to like the positive half of the board. You know, it doesn't account for everything under 0,
Right.
the point. So does that mean if we want to find the absolute every piece of the board that's light, we actually have to do y bright times 2 because y bright is only the top half, right?
Yes, yeah, you have to if you're looking for like the width of like if you have like a central fringe here and you want to look at its width, the width will be 2y.
Okay, I see. Okay, thank you, sir.
No worries. Yeah, I think this is actually a question in the chapter of the textbook that talks about that, how to find the total width, yeah, you just have 2y, so you have to do 2l, and then m would just be the first order fringes, that's just 1 over lambda d. Okay. Oh yeah, and if you know everything else, you can measure the wavelength. In the lab, we knew the wavelength. We didn't necessarily know the spacing. So, yeah, you can also find the intensity, which is a co-squared function. It's squared because it doesn't go into the negatives. The intensity goes from a maximum to a minimum of 0. So if you graph that, you get up and downs. It's kind of like a roller coaster. And you get the maximum intensity at the bright fringes and 0 intensity at the dark fringes, and everything between is kind of like a gradient. This is the only intensity formula you might have to know. Don't worry about the single slit intensity or the combined intensity. So in the diffraction grading, you have way more slits. That doesn't change the location of the bright fringes. That's why the formula I said for Y bright works for both double slit and diffraction grading, because the adding more slits just makes the fringes thinner, but it doesn't change the location. And adding more fringes also causes like little secondary maxima, but don't worry about that. So you saw that like when a wave, like a mechanical wave hits a hard wall, it gets reflected upside down. So the same thing happens for light. When it hits a hard boundary, it's gonna get reflected out of phase. And that's what causes interference. So here you see it. A hard wall, like the person holding on the rope, makes the wave get reflected back upside down, so that's out of phase. But it's a free end, no problems, comes back the way it came. Cool. So same thing happens with light. That causes some thin film interference. Let me just summarize this with a cool website I found. Where am I? Where did I have this? Ah, yes. So consider this case. Consider the case where the light enters into a new medium N1, and now it comes out another medium N2. Now, in a situation where both the first medium and second medium act as a hard wall, both rays that emerge are actually in phase with each other. So this ray here that's coming out of the second media gets reflected out of phase But this ray that hits the first medium also gets reflected out of phase. So if they both get reflected out of phase, then they're both at phase relative to each other. So the only thing that's going to determine their constructive or destructive interference once they reach your eye is the path difference. The path difference is just how much extra distance this ray travels when it enters the medium. We do a quick and dirty approximation where, like, if you look at the distance traveled, there's some vertical and horizontal displacement, but the assumption is that this horizontal component of travel is tiny compared to its vertical component. So we just look at the vertical component to determine the path difference. If you look at it, then you have to travel the thickness of the medium and then travel the thickness of medium back up to then emerge. So effectively, your total travel distance is twice the thickness of the medium. That's what sets you apart from the other ray that just hits the boundary and doesn't go in. So twice the thickness of the medium is the path difference between the two rays. And if they're both in phase, then as long as there's some integer multiple of the wavelength, then they're going to construct, they're going to do constructive interference. Be careful though, because while the ray travels inside this medium, its wavelength changes. So you can't just use lambda, you have to divide lambda by the index of refraction of that medium to do it properly. Now, for destructive interference, well, the path difference just has to be a half wavelength integer. So n plus 1/2. Now, there's another case though, where one emerges out of phase and the other one doesn't. This happens if the medium here, let's call this medium here NO, N1, N2. So this ray here undergoes a phase shift because it's hitting a wall. NO is smaller than N1. This ray coming in here is not hitting a hard wall, so it doesn't get phase shifted. So in other words, whatever medium it hit, its index of refraction wasn't as big as the incident medium. So in this case, this ray here emerges in a different phase than the ray here. So you have a ray coming in phase, you have a ray coming out of phase. So the conditions for constructive and destructive interference now get flipped. If the path length is now a half multiple, that makes constructive interference. And if the path length is an entire multiple, that makes destructive interference. And you can kind of see, right, how, like, you know, they're like emerging kind of like aligned with each other. So it's gonna, so what's gonna like determine if they construct or deconstruct, it's again the path difference. So yeah, it gets flipped. So you see how like the formulas are now the opposite of each other because one of them is out of phase. So two cases. Either both get flipped or only one of them gets flipped. And that respectively flips which formula is for what. So I think in the case of like what was it, oil, if you have like air, then you have water. No, you have air, then oil, then water. Because oil is the thickest of the three media, only the beam that hits the air-oil interface gets reflected out of phase, but then the beam that hits the if you hit the beam that reflects off the air-oil interface gets reflected out of phase, but the beam that hits the oil-water interface gets reflected, the phase doesn't change because the index of water is less than the index of oil. Now, where did I? It's gonna be, I think it's gonna be like 2 questions on thin film interference. So. Okay. So I'll quickly talk about the rest. So that's all the slides you can find in Omnibox. So for mirrors and lenses, you have a formula that tells you how to locate where an image is created based on the position of the object, and you just also need to know the focal length of the mirror. So you have to be careful though, because normally the object distance P is a positive number, but the focal length and the image distance that you get can be negative or positive depending on what side of the mirror or lens they're on. So for a mirror, being on the same side as the object gives you a positive sign, but here behind the mirror, that'll give you a negative sign for the image location and focal length. So concave mirrors that focus light, they have a positive focal length, and convex mirrors that disperse light have negative focal length because it appears behind the mirror. So virtual images, and which is an image that appears behind the mirror, it's going to have a negative object location. So you should know what a virtual and real image is for lenses and for mirrors. You should know when an image is going to be upright or upside, or you should be able to determine how an image can be upside down or upright. The way you do that is if you look at the magnification formula, right, which is just m is equal to, you have this on your formula sheet, the object image distance over object distance. If this is negative, if you get a negative magnification, that tells you that the image is upside down. And if Q is positive, that tells you that you're dealing with a real image. If Q is negative, that tells you you're dealing with a virtual image. And also M is a magnification. So it tells you like by how much the image gets scaled. So that means that if M is bigger than 1, that means that the image is going to be bigger. And if M is less than 1, that means that the image has shrunk. The image looks smaller. So you can kind of see some examples here of like, if you put an object close to a concave mirror, it makes a tall image. And you can see in the ray diagram how the rays converge at such a point where things look taller. So just know thin lenses. This formula, don't worry about it. Just know this is a lens equation, same as a mirror equation. Be careful with Q and F. So just know for what type of lens F is positive, what type of lens is negative. So there's a really nice summary here of what a virtual image is. So in this case, if the image is formed across the lens, it's actually going to give you a positive value of Q. Same with F. When F is across the lens, that's a positive focal length. It's all explained in the table below. Ba-ba-bum. Okay. So don't worry about systems of lenses. And then we're gonna get kicked out soon. So don't worry about this formula. Don't worry about the intensity of the single slit diffraction. But just know for the single slit diffraction, you have a formula that lets you find the position of the dark slits. Again, it looks similar to the position of the bright fringes for the double slit or diffraction grating, but this one is actually with the dark fringes. So be careful with the distinction. And then the small angle approximation can be done here, so you can end up with a formula like I showed you before, where you have like bright is equal to L lambda over A. But even without the approximation, it doesn't really. You can just say that sine theta is approximately the y over L, since you're assuming that hypotenuse is dominated by the length L, so you can just kind of figure it out how like L sine theta will give you a y. But the small angle approximation is valid. And there's an example here we're talking about, like if you want to find the width of the central slit, you just do 2L sine theta.
Sir?
Yeah.
Like for diffraction patterns, like is there like a sine theta light equation, or is it just sine theta dark?
There is, because that would just be like a half integer distance, but we don't use that for single slit diffraction.
Okay.
We just talk
Would
about
it be like
fringes.
half of A? So it would be like A plus a half, or where would the half go?
Yeah, I guess the path difference would be A sine theta dark. Probably the same setup where you have M plus 1/2 lambda. So, wait a minute. This is the theta. This is not theta dark. This is theta light. Yeah. Just not normally used because for physical measurements, you want to find the dark fringes to measure the width of the bright fringes. So this is why this formula is not really used. Anyways, we're gonna get kicked out in 1 minute, so I'm gonna follow up with the questions you've had. I'll send you a note. I had that question about the open stacks, question 29, so we'll follow up with that. Any last thoughts before we get kicked out? Don't worry about this intensity formula. Don't worry about this one either. Don't worry about this. Don't worry about the limiting angle. That's not gonna show up. And just know the diffraction rating. Know that it's the same formula as the double slit diffraction, just sharper peaks basically. And that will actually be all you really need to know. So we're gonna get kicked out in a minute now. So yeah, I'm gonna call it a day. If you have any more questions, just let me know. Again, I put up these slides, I put up the formulas you're gonna have. So just be careful because we talked about all the formulas today, not all of them in the formula sheet. So remember what you might not see there. Anyways, let you all go, and we'll see you on Friday. Good luck.
Thank you so much. Have a good day.
All right, thanks, you too.
Thank you.
You're welcome.
Thank you, sir. Sir, are you going to post a recording?
Yes, as soon as it's finished uploading, I'll make sure to put it up on YouTube.
Thank you.
Thank you.
No worries. All right, we're way over time, so I'm gonna let you go on to the next class. All right, everyone.